Hello, precious friends. I hope I find you well and happy today. Today we are going to be looking on what you call functions. So I don't want to waste time. The topic is there on the screen and whatsoever we are going to be doing. So what I want you to do is to be part of the family if you are not. So just you have to do this if you are not part of the family. You only need to subscribe and also click the notification button so that whenever we upload content on this YouTube channel, you get it while it's still fresh. Okay, I don't want to waste time much, on introductions. Let us jump into the topic first and see exactly what does the video contain for us. Okay, so to start with the definition, a function is a rule used to convert an input value into an output value. Meaning to say, whenever I have a number which is an input, it can be converted into different outputs by means of a certain rule, and that rule is what we call a function. Okay, now we have got four types of functions, of which two of them has to do with asymptotes, and I'll let you know what is an asymptote as time goes by, and then the other ones has nothing to do with asymptotes. So the functions that we are going to deal with in this video are four, which are: number one, we have what you call the linear function; number two, we have got what you call the quadratic function; number three, we have the hyperbolic; and number four, we have the exponential function, which are the functions that I'm going to put here in breakdown: linear, quadratic, hyperbolic, and exponential functions. Okay, so what you may say is, okay, now we have got four functions and we now know them, but how do we know that this is linear, this is quadratic, and this is hyperbolic, and so forth and so forth? That one is not much a problem. Let me show you. They have got what you call the nature of the function, and also they have what you call the type of graph that has to do with the function. Let's get into it. Okay, so as it is on the notes, you would find out that we agree that linear functions are functions of the nature y is equals to x, and then quadratic functions are the functions of the nature y is equals to x squared. Hyperbolic is y is equals to 1 over x, and then exponential functions, they've got the nature y is equals to a certain number, then to the power x. Let us consider that in examples. All right, so what you need to do is to try and find exactly what these mean. So let us consider this example for linear functions. These are what you call the mother functions. By the way, let me start by saying these are the mother functions. Okay, mother functions. Okay, so for a linear function, we said that the mother function is y equals x. All right, so this is what you call the mother function. And then if it is quadratic, we have got something like y equals x to the power 2. That's the mother function. And then number 3, we have the exponential, the hyperbolic, which is y is equals to 1 over x. And then finally we have the one that is got a power, which is y is equals to any number to the power of x. Okay, now I just want to try and exemplify or show you exactly what it means when I mean n to the power x. When I mean n to the power x, if you hear something like y is equals to, let me pick any number, let's say 5 to the power x. Okay, this is a good example of what you call an exponential function. Okay, let's say also sometimes they put it in this nature, y is equals to, and then the number is a fraction. Let's consider maybe 1 over 5, and then here we put to the power of x. Okay, all right, so these are the mother graphs that we have, and I want to show you exactly what they look like when they are sketched on a graph. So the first thing is we need to start with what you call the mother function of y is equals to x. All right, when we have y is equals to x, the graph is like this, okay, meaning to say the graph is a straight line which cuts the axis, which is the y-axis, and the x-axis at a point of origin, which is 0 0, and it kind of divides, you know, this graph into two equal parts. All right, that's what you call a linear function, and that's the nature of a linear function. Let us consider what you call a quadratic function. A quadratic function is got also this nature. So the nature of a quadratic function, it is like a U shape, okay, or a smiling shape, like this. All right, so it has got its turning point exactly on 0 here, okay, so meaning to say it touches, or it turns at the point of origin, and it forms a cup. Then from the quadratic we have what you call the hyperbolic function. Can I just stretch it this side? All right, and then now for the quadratic, it has got this nature. For the hyperbolic, now the hyperbolic has got two graphs that are drawn. You'd find out that as we agreed that hyperbolic, now they are now dealing with asymptotes, okay. Asymptote, okay, so an asymptote is a line in which the graph will not touch. So here, what are the asymptotes? If we consider this hyperbola, you'd find out that the y-axis is an asymptote and the x-axis is an asymptote, meaning to say our graph will not touch the y-axis. So it may come closer to the y-axis, but will not touch the y-axis. When it goes down, it seems to not touch also the x-axis, meaning to say it won't cross the x-axis, and here when it's going up, it won't touch or cross the y-axis. So here it here's also the other part when y is negative, because here we were considering the positive side. Then the negative side also does the same thing. It tends not to touch the x and the y-axis, meaning to say when it's going down, it doesn't touch. When it's going also up, it won't touch the x-axis. So this is the nature of what you call the mother graph of a hyperbolic function. So both x and y are asymptotes. Let's consider now the last one, which is the exponential function. So for exponential functions, we have got two types of graphs here. Let's start where the number is a whole number. You would find out that when the number is whole, okay, the nature is a rising graph which cuts the y-axis at the point where y is 1. But if this number is a fraction, we have like a falling graph which touches or crosses the y-axis at the point where y is 1. So that's the difference. Here, if it is a fraction, then it must be falling. And if it is a whole number, then it must be rising. So please note that the 40 part or the 40 type, which is this exponential function, it has got two types of graph, the rising one and the falling one. But the secret about them is that they both touch, or they both crosses the y-axis at a point where y is 1. And then what is the asymptote? The asymptote is the x-axis, okay? All right, so meaning to say we'll have our x-axis as an asymptote. So this is what you need when it comes to the issue of sketching graphs or sketching functions. You need to know the nature of the mother graph. Okay, whatever that you're going to do, be it a transformation or whatsoever, notice that you are going to be dealing with these mother graphs first, and then you do transformation. Let us now consider how do we transform these graphs. Okay, now talking about transformations, let us consider how do we describe the transformations. So here I have the rules of transformations, which are stretch, reflection, and we have translation. Okay, now we need to consider the rules themselves. All right, so let us just do this. All right, I can't be using notes here. Let me just show you the rules one by one. Okay, so as you have seen, from the previous page, okay, let me just go back. You would find that all the mother functions are showing us only one thing, the relationship between y and x. We only have the variables y and x related, if you can see here. And then here we also have y and x related in that nature. So meaning to say there is no any other plug-in or any other guy that you are seeing here. So what does this mean? This means, okay, when we put another extra number to these functions, we'll end up having what we call transformed graphs. So let us try and put those extra numbers. So in these transformations, we are going to consider only two special numbers. All right, so the two special numbers that we are going to consider are number one, what you call the coefficient of x. And then number two, what you call the independent variable. Okay, so what are they? Let us consider this example. We had the function y is equals to x. And then we agreed that this is the mother function of what you call a linear function. Okay, so now when I put a coefficient on x here, you'd find out that my function becomes y equals ax, where a is any number that's going to act as a coefficient. Okay, and then after that we need to consider the independent variable. The independent is a standalone variable, like what we can put a number that is not attached to x, which is, let's say, plus b. So here, if you look from the mother graph, we have inserted two things here. Number one, the coefficient. Number two, the also independent variable. This is what makes the difference between the first and the second function. Okay, so this one and this one are made different because of Mr. A and Mr. B. Okay, so we need to look at what effects does putting a coefficient have, and what effect does putting an independent variable have to our graphs. That's very good. Let us consider that. So the first thing that I want to tell you is that whenever you put a coefficient will stretch your graph. And then when you are stretching it, meaning to say you are making it either thin or you are making it thicker. That's what you call stretching. All right, and then what about B? The influence of B to our mother graph is that B will shift our mother graph up or down. Okay, so meaning to say here, we are doing all these functions, or I mean transformation, along which side of the graph. Okay, I want you to notice that when A gets big, okay, here when A gets big or when A gets smaller, we have these rules. So the stretch says that when the value of A gets big, which is the bigger the value, the thinner the graph. They tend to be a little bit opposite then, eh? So bigger coefficient leads to a thin graph, and then smaller coefficient here leads to a thicker graph. All right, and then here, what about B? Okay, the bigger the value of B, the graph will move up, but then when the value of B is smaller, then the graph moves down. We need to consider that exactly using a certain animation. So let me quickly show you how do we transform these things using maybe a picture. Okay, so as I have said here, guys, I just want to show you something. You would find out that here we have okay, let me just do this. So we have got our graph here, and what is the function of the graph? This is what you call f of x is equals to all right, this is what you call f of x is equals to ax plus b. All right, so this is at this moment a mother graph. Why? Let me just show you that we can remove the function of b and a and remain with the same graph. So this is the graph of y is equals to x, which is a straight line. As I said, if you can see here, we have the value here is x. Okay, you can see we have an x there, and then here we have f of x. F of x is y. So this is what we consider when we are talking about the mother function. All right, now besides that, we see that we have put here some kind of plug-ins to this function, and these plug-ins, the first one is you can see we have plus b here, and then we have another plug-in which is a. These guys, what are they doing to our functions? Because in the first place we only had f of x and x. All right, so what they are doing is a is trying to make our graph thin, and then b is going to shift our graph up. All right, let us consider that in practice. Now I have a number line that I'm going to use here. This is the number line indicating the changes in a, and this is a number line indicating the changes in b. All right, let us consider those changes very quickly. All right, so as the value of a gets bigger, as I said, we move to the right. Okay, as the value of a gets bigger, the graph is going to be thin, and then when it gets smaller, the graph is going to be a thick graph. All right, so meaning to say when it gets smaller, the graph is going to be thick. And then when the value of b gets bigger, as I said also, that the value of b can get bigger. Okay, when the value of b gets bigger, the graph itself gets it moves up, and then when it gets smaller, the graph will move down. Let us do that right now as an experiment. Okay, so I want you to be looking on this slider, and then on this also slider, as we'll be doing the transformations. Let me now clear the board so that it can be clear. All right, now what we have is, this is my mother graph. All right, when I increase the function, or when I move and make a bigger, let's change the value of a from 1 to 3. Do you see this? The graph is becoming thinner or smaller. Why? Because you can see here that the graph itself is coming close to the y-axis, and then if I take and stretch it also closer, 5, it is becoming very, very thin. But the moment I reduce it from 5 to 3, is opening, meaning to say is becoming a fat graph, and then I come here, when it's now 1, you see it's now fatter than when it was on 5. So this is the effect of making a big number and making a smaller number. Let us consider what is the effect of making b a big number and making b a smaller number. Now you see that b is 0, By the time I change B from 0 to 2, the graph is going up, and then I take it. Now 4 is big, and now it's big. Now you see when it's 10, it's moving up, because okay, how do you see that the graph is moving up? You consider what you call the intercept, or the y-intercept here, the position where the graph is cutting the y-axis. Okay, let's do that. You see the y value is decreasing, meaning to say it is the movement down of the graph. Now we are on 0, and then we go up. We are increasing the value of b from 0 to 2. It moved up 2 units, and then 4, it moved up 4 units, and then 6, it moved up 6 units, 8, 10. That's the secret of changing the value of b. Okay, now let's go back and see exactly what will happen if we change the value of a to a negative. All right. Now I have had reserved this. When a is a negative, okay, then it means the graph is going to be what? Is going to be reflected. So the negative sign, or the negative sign then on a, is going to show what you call reflection using the x-axis as a mirror line. X-axis is a mirror line. All right, that's the rule. Meaning to say here, if my graph, let me take it for example, was this way. All right, now if this one is a mirror, I know that most of you guys have been looking at yourselves in a mirror. If this was a mirror, let's say this was you. Okay, let me just draw it like this. Let's say this was you, and maybe this is your nose, and then your mouth, something like this, and then that's you maybe. Okay, you are in a mirror. All right, you would find out that the mirror is a reflection of you. It seems you are looking down, but when you're looking down in the mirror, your reflection will be looking up, meaning to say your reflection is exactly a total opposite of you, and then it will be like this, and then and then your mouth also in that manner, right? Something like this. Let's say that's your mouth, and it just goes like this, and then all right, like in this manner, and then this becomes your reflection. So we say this is the reflection, and this is the object. Okay, so graphs also do the same thing about the x-axis, if and only if they are if their coefficients have got a negative value. So this is what you call the positive graph, and then this becomes what you call the negative graph. So meaning to say, if my graph is like this, and then I say this is the positive graph, then the negative graph will be like this. That's the difference between the issue of reflections. Okay, and this becomes the negative graph, which is a reflection. How do we consider that? This means the negative value of a, and this is the positive value of a, gives a difference. Using the x-axis as the mirror. Please don't forget that this is going to be used as your mirror. Let us consider that also in practice. Okay, so as we can see here, what does this mean? This means if we use our x-axis as the mirror here, what is going to happen is from here, all right, this value is a mirror. So if you're considering the right side, you'd find out that this one was going up. Now in the mirror it must be going down like this, you see. All right, and then this was going up. In the mirror it must be going down. So by the end of the day, what will I be having? I'll end up having, all right, now let me do this. I said this part, this section of my graph is going up. All right, now what I have to do is to change it and make sure that it goes down. All right, okay. I think my pen is misbehaving here. All right, so to make it go down, this means this part should be going down. Okay, let's go down, don't mind. And then this part which was going up also needs to be going down, and then this becomes the reflection of my graph. So this is how I get a reflection. Who is the mirror? This x-axis is a mirror that I'm using to reflect my graph. Okay, so if I draw this part and say this x-axis, all right, yeah, this one is reflecting the green one to the black one. I hope you found it understandable. Let us do that exactly using the perfect way of practicing it. Okay, so let's consider a was +1 here in this case. What if we change a and make it a negative value? Look what is going to happen now. I'm going to move my slider to the negative side of the number line from +1 to negative. That's it, exactly the line that we have drawn, the black line. And then now, what is the effect when the digit value of a increases? Meaning to say here, when the digit value of a increases, we are going to see that our graph tends to be skinny also, or to be thinner. All right, meaning to say if we are moving from 1, we are on 3, is getting skinner, and then here it's on 5. Now it's very, very skinny. You find out that our graph is almost vertical. So it got thinner because of that. All right. Now when we are just reducing from 5, let's go 3. And then -1, you see, is now a fat graph. So these are the rules of transformation that we are going to be using for the two graphs that has no asymptotes. All right, let me summarize those rules in this part of the screen. Okay, number 1 rule says that a coefficient is a vertical stretch vector, meaning to say the bigger the coefficient, the closer the graph is to the y-axis, and the further it goes from the x-axis, meaning to say the bigger the coefficient, the thinner the graph. And then let's consider the other rule. It is saying a negative sign reflects the graph about the x-axis, meaning to say every coordinate of y must change. Okay, that means the x-coordinate remains unchanged. Don't mind about the other part of the explanation. Just tell yourself that a negative sign reflects the graph about the x-axis. And then there's another rule then that we need to talk about. What is it all about? It is about b now, meaning to say an independent variable b. Okay, what does that do? It describes a translation, meaning to say the graph will be shifted up if b is a positive, and will be shifted down if also b is a negative. Another thing that I want you to know is that b, which is the independent variable, always or also shows what you call the y-intercept of your graph. Okay, but we are going to follow these rules when we are dealing with linear and also what you call quadratic very much. I'll show you some kind of adjustment to these rules when we are dealing with those lines that has got, or those functions that has got asymptotes in them. All right. So, okay, once more, allow me to show you how am I going to be using this application. All right, trying to summarize everything. So what you're going to do here is we are going to show, as I said, that here on this section of my graph, I'm going to indicate the function that we'll be dealing with. All right, and then here on this slider, I'm going to show you what you call the changes that's taking place in A, and then here I'll show you the changes that's also in B. So the graph itself is going to be indicated by this green line. All right, so you need to consider these 3 things. Okay, the sliders, the function, and also the changes in the graph. So try and get yourselves with greater concentration, so that whatever that's going to happen, you will also kind of notice is as early as possible. So let us now change the function. For here we had f of x is ax plus bx plus b. Okay, we need to change it now from the one that is x to the one that is x squared. Let us replace x by x squared and see what's the nature of the graph. Okay, so this means here on x, I'm going to replace x by what? I'm going to put here x to the power 2. Okay, so now we have x to the power 2. Okay, right, look here, the challenge is my a was a negative, so it was supposed to be this way when a is positive. Now we have a being positive 1. All right, so when a is a positive, the graph is facing down, it is cup shaped. And then when a is a negative, look, the graph, it just have shown me the other part, which is the same thing that we were talking about. Is called a reflection. And we said that when we multiply the input, which is when we multiply the input value by a negative, the graph itself is reflected about the x-axis being the mirror line. All right, let us consider now when it was a positive. Let's say we want to see what will happen if we increase the value, as we said that when we are multiplying by a coefficient, okay, which is the vertical factor. What is the rule? The bigger the coefficient, the steeper the graph. All right, and the steeper the graph's arms. Okay, let's consider this. Let's change it a little bit. Oh, to 3. Now it's becoming skinny. And then we go ahead. 5 is now skinny. It's very, very close to the y-axis, if you can look at it. But the moment I decrease from this and then go there, all right, you'd find that my graph is opening up, it's getting fatter. All right, let me try and change these values maybe so that we can also move. All right, let's move from 5 and try and increase it to 10. And then here from -5, we need it maybe to something like -10, so that maybe we can visualize it the better way. Okay, fine. So meaning to say here when it is 1, okay, 2, 3, 4, 6 here, 8, look, 10 is now very, very close to the y-axis. If you can look at this, you can say if it was a human being, then you say these are the thin people. And then if we are here now, let's say we are reducing the coefficient now, you'd find out that if it was someone, maybe you would find out that the person is getting fatter and fatter as we reduce the coefficient. Okay, now let us look at the changes when now we shift b. We said here when we are increasing the value of b, that's what you call translation. Okay, adding an independent term to the input value in the mother graph will shift it up or down. Let's go. When you move to the right, we are increasing. Okay, that's the story. The graph is moving up and it is going up and up. Okay, now let us move to the left, reducing the value of b, which is we are decreasing it from 10 to 8. It's going down. Now it's 6, down, 2, down, and then let's go. It's now on 0. It's going down again. The more we move down, the more we move further and reduce the value, we would find out that the graph is moving down. So you'd find out that the rules of transformations are the same. Only that the graphs are the ones that are different. So what you do to transform is the same thing, okay? For all the graphs, we are sticking to those rules also. All right, let us consider now the other function. Here we want to change the value of x, because here we were having f of x is x squared. Now we don't want f of x is x squared. We want to move from f of x is f squared to f of x is 1 over x. Okay, look at what the graph is like, exactly as we have drawn there. Now, when f of x is like this, I said the graph will come closer to the x-axis, will not touch it, come closer to the y-axis, will not touch it, in the same manner that what is happening to the positive is happening to the negative side. But let us look now. When we have asymptotes, there is some kind of changes that I want you now to notice. As long as we have asymptotes, the moment we increase the value of a, the graph tends to go further from their asymptotes. All right? You see, they are going further from the asymptotes, further from asymptotes. Now, 8, 10. They, instead of them getting closer to y alone, they get further. They tend to go further from the asymptotes when the value of a increases. Meaning to say, when the coefficient increases, they tend to go further from the asymptotes. That's the rule. All right. Now, let's consider b. What is the effect of b? I want you to notice that when I shift b, the rule is the same. Increase in b will move the graph up. Meaning to say here, when the graph is moving up, you need to notice that the asymptote is also moving up. Here, look. In the first place, the asymptote was x-axis, which is, it was not touching the line y is 0. The moment I move it a little bit up, it is not touching the line y is equals to 2. Meaning to say, when I shifted b 2 units up, the graph moved up, and also the x-axis moved from 0 to 2, meaning to say it is now on 2. The moment I move it up, it's now on 4. Move it up on 6, on 8, and on 10. Meaning to say, as the graph is moving up, the asymptote also moves up. When the graph moves down, the asymptote also moves down. That's the rule. All right. Now, let's consider the issue of reflecting by changing the coefficient of the the sign of the coefficient. Automatically changing the sign of the coefficient will reflect your graph about the x-axis. That's what we agreed on. So meaning to say, the moment this one becomes a negative, look at what happened to the graph. Now it moved. What was on top went to the bottom, and what was at the bottom went to the top. Why? Because we are using our x as the mirror line, but the rules of then the numbers is the number or the digit gets bigger, the graph tends to be further from their asymptotes. That's the secret I want you now to understand, that the bigger the digit of a, the further the graph from its asymptote, and then the bigger the coefficient of a, or the bigger the digit of coefficient a, the skinny or the thinner the graph becomes. All right, these are the symbol rules that we need to consider. All right, let me just go to the positive side. Okay, let us now change to the last one. As I said, I just want you to have a picture of it. Okay, we said that we have a graph also whereby now we'll have any number, let's say 5, raised to the power of x. Okay, and then let's check what the graph will be like. That's what you call an exponential function. And now you'd find out that with this exponential function, the graph is rising after crossing here. It is going rising the way, all right, up. So why? Because we said that when the coefficient is a whole number, the graph tends to go up. What about the rule of a? The rule of a also is the same, because here there is an asymptote x. The more we get bigger here, you see, is the more it tends to run away from the asymptote. All right, but the moment we get it smaller, it tends to be attached to its asymptote. I want you now, you cannot see that the graph is running away from its asymptote because it has got a very small space there. But now what you can do is consider this angle that it is going to shift itself up the more I increase the value or the digit value. Look, it tends to rise from the angle that's going away or going further from the asymptote, which is x. Let's consider that again. Look, it's trying to go further from the asymptote. That's the effect of increasing a. When the value of a gets bigger, then the graph tends to run away from its asymptote, only that it has got only one asymptote. But now this one can also clearly be a conjunction of also the two rules. The moment I'm increasing the value of A, what are you seeing about the graph? It is coming closer and closer to the y-axis, so it's getting skinny. At the same time, it is moving further from the from the from the asymptote. Okay, what about B? The same rule. B shifts it up, meaning to say the asymptote also shifts with the graph. That's what you need to know, that the moment you shift the graph up, do not forget to shift the asymptote. Here the asymptote was the x-axis, which is y is 0, y is 2, y is 4, y is 6, y is 8, y is 10. The graph is not touching those. And then when you go down, same ways, okay, y is minus 2, minus 4, minus 6, meaning to say my graph will not touch these values, all right? Though in this case, people will say, all right, so why is the graph now cutting the x-axis? Okay, automatically to cut the x-axis because the x-axis is no longer the asymptote when the value of b is negative 10. The asymptote becomes negative 10, which is also what we were expecting by that time to be the y-intercept. Just take it that way, all right? It will not touch the asymptote. All right, now let me come to the situation whereby now the value of the number itself was changed maybe to a fraction and then maybe to 1 over 5, and see what will happen. Look at the graph is exactly the same, but by that time it was rising. If you have seen it, it was rising like this. It was coming from here and then it did cut here and then went up. But now when we changed from a whole number to a fraction, we find that the graph itself was reflected about the y-axis, meaning to say it was changed to face the other way around. That's the difference. So when it comes to the transformation, the rules I can't repeat. It's the same thing also about the transformations, meaning to say by the moment I increase it, you see it goes further from the asymptote and coming close to the y-axis. The moment I make it a negative, it then is reflected about the x-axis, meaning to say the mirror becomes x. And then what if I shift b shifting it up, also the asymptote moves up and then moves also up or down, all right? That's the same rule that you need to consider, all right? Fine. I think with this I'm done with the stories of transformation and also the stories of the mother graph. What I have to do is just to try and summarize this topic, okay? I hope you did understood the effect of this independent variable, and also the effect, okay, we said this is the independent variable, right? And then, so I believe you have understood very well about the effect of my independent variable. Sorry, what's happening here? All right, so my independent variable has got an effect, and then also A has got an effect, okay? So the effect of the independent variable is that it moves my graph up, all right? Or it moves my graph down, all right? And then what is the effect here of the value, which is the coefficient? The coefficient tends to move my graph, not up by the way, okay? It just makes it skinny, all right? It tends to make it go skinny, all right? Yeah, it makes it go skinny, meaning to say it tends to move closer to the y-axis, and then it tends to move also away from the asymptote. That's the effect, all right? And then the four functions are well, you know, represented here. This is all, guys, about how do we transform these graphs. Let me just quickly write these things down for you, okay, so that you will remember them in a summary. Okay, let me just go onto the fresh page here. So we say that every function has got what you call the mother graph. What is important is that you know the formula for the mother graph and also its sketch. And then from the mother graph, we have got what you call the coefficient of mother graph, okay? Coefficient of the mother graph. So the effect of the coefficient is that the bigger the coefficient here, the bigger the coefficient, or the bigger the digit, okay? In the coefficient. All right, the thinner the graph. The thinner the graph, or the further it goes from its asymptotes, okay? So that's the rule of the coefficient. Then there is another rule, which is the second rule of also the coefficient. A negative coefficient is a reflection about the x-axis, meaning to say the x-axis becomes the mirror line. All right, that's fine. And then let's consider then the other part. What is it? Which is b, all right, which is the independent variable, because every mother graph must have an independent variable. All right, the independent variable, what is the effect of the independent variable? We agree that the independent variable has got a very simple effect. It causes the graph. Oh, sorry. It causes the graph to move up, okay, up or down, depending on whether the independent variable is a positive or is a negative, okay? So the moment we are moving up, we are adding, and the moment we are moving down, we are subtracting. All right, so these are the important parts of how we transform the mother graph, okay? So this is the mother graph transformations or transformation rules. Okay, let me not waste time here. It's almost 48 minutes. Yeah, this is a long video. So we have to find the mother graph first, and then after finding the mother graph, what we need is to show the transformation which was brought by the coefficient. So the coefficient brings number 1, a reflection, number 2, a stretch, number 3, we have what you call the independent variable. It brings an upward or a downward a movement of the graph. These are the three things. Let me consider one example here or two of them. All right, so here on the screen we have examples which are reading here. Okay, sorry. Okay, describe the following functions. Oh, describe how the following functions are transformed. Let's consider here we have got y is equals to negative 2x plus 4. Y is equals to negative 2x plus 4. The first thing that you need to do is just to highlight your mother graph. So your mother graph is y is equals to x. Alright, so since it is y is equals to x, what do you see here? There is this guy coefficient, and there is also this independent variable. So what is the independent variable doing, and what is the coefficient doing? So the first thing is we see that the coefficient is a negative here, so we say there is reflection about the x-axis, okay, and it is indicated by the negative sign, okay. Then we move on, number 2, the graph. What is happening here is the digit 2 is greater or is bigger than 1, so this means here we got a bigger coefficient, so the graph is stretched towards y-axis, all right. To say stretch towards y-axis is what you call thinning the graph, so it was made thinner, all right. So it was stretched towards the y-axis by the stretch factor, okay, 2. You see, so 2 was stretching it close to the y-axis. Why? Because this one is a big stretch factor, it is bigger than 1, okay. All right, fine. And then now what is the third transformation that we are seeing here? There is also a shift on 4 there, which is the graph was translated, because the translated, let me not be talkative, okay, 4 units up, okay. Why 4 units up? Okay, automatically the 4 is given, but up is indicated by the positive sign. So these are the descriptions that you need when they say describe the transformation of y. Okay, let's say here we have y is equals to x, which is the mother graph, to this function. Let's consider also the next question, which is saying describe the transformation of y is equals to minus 2x plus 8. So we have y is equals to minus 2x squared plus 8. Don't worry about it, you have to consider also your mother graph. So what's your mother graph? Your mother graph is connecting these two variables only. This becomes your mother graph, so it's y is equals to x squared. And then what do you see? Oh, the same guys here and also here. So what do you see here now? Reflection about the x-axis. Why? Because the coefficient is a negative. The coefficient of x squared is a negative, all right. Now consider the other thing here. We have got 2, which means what is this 2 doing? The coefficient of the coefficient of x squared is bigger than 1, so we have got a bigger coefficient, which is 2 here, is indicating that the graph should be skinny, all right. Oh, sorry, skinny, but you are not going to use these terms. You are going to be using terms like the graph is stretched towards the y axis. Okay, that's it. So the last part is this plus 8. What is it? It's a shift up, okay, because there is a positive sign. Okay, we don't want to waste time. Let's consider what the graph will be like. So the first thing here, we had this graph, okay, which is the mother graph, y is equals to x squared. And then now it was reflected, which is it was changed into this one, okay. After that, we are done with this issue of the minus sign. And now we need to move to the next transformation, whereby we are now taking it closer to the what? To the y-axis because of the coefficient. So we are now taking this one closer to the y-axis, making it thin. After that, we have to shift it 8 units upwards, meaning to say here it was on 0. When you shift it 8 units upwards, it was on 0 here, right? So it moves from 0 to 1, 2, 3, 4, 5, 6, maybe 7, 8. Alright, if the graph was going up like this, meaning to say I'll have a thin graph now cutting the y-axis at the point 8. That's what you do. So when they need you to draw this graph, this becomes your final answer. Very simple. Alright guys, let me not waste time. I don't want to reach an hour here. If you have questions, just hit me inbox. My account is there, gracewatersacademic.tutors@gmail.com. Okay, so you just send a message there or whatsoever. Just contact me so that maybe we can also help you with further explanation. As for now guys, this lesson I can say it's ending here. If you are not part of the family, it is also my advice once again that you become part of the family by simply clicking the subscribe button and also that bell button to get notifications whenever I upload content. God bless you. Let's meet again. Sharp.